when you have in the same environment a lot of different languages that work together, and that this creates a lot of overhead. Second thing is the GraalVM. This is actually the main topic of my speech, and this is actually a virtual machine that solves some of these problems. Next, I'll be talking about Truffle. Truffle is actually a part of the GraalVM project that deals with implementation of different languages into the GraalVM system. Next will be the Graal, the JIT compiler. So this is the compiler that is actually inside GraalVM. Then I will present my role in all of this project, my tests, what I did with this Graal, and the results compared to the standard JDK. And then I will mention additional features, and at the end we'll have a Q&A session. So polyglot problems. Cross-language operability, what does this actually mean? So for example, you have a large project and you want to solve your specific programming problem with some language that solves this problem in the best way. But on the other hand, you're using, for example, I don't know, Java, but for this particular problem, you want to use different language. And when you want to use this data needs to be marshaled and serialized and sent via some interface. And on the other side, you need to deserialize this data in order to use it. And this creates a lot of overhead and causes performance losses. Second problem is general purpose programming languages aren't as optimized as the ones that achieve high industry attention. So for example, if this language is used like really in industry, a lot of time and money will be invested into this in order to work really good. And the third problem is the language tools. So the runtime-based tools as configuration tools and debugging tools. The problem is that a lot of languages don't have really good tools and debuggers, and some of them don't even have it at all. And if they come pretty late, and you cannot really use them. So what would you really want to have is to have like a set of tools that can be used in polyglot manner. So you can use like a JavaScript debugger in Java or something similar to that. And I also put this table that shows the usage of programming languages, which I want to emphasize that there isn't like an ultimate language that can solve all of these problems. So you have to use different languages to combine and to fix your problems. So GraalVM. GraalVM is the main topic of this project, and it is a virtual machine. And this project started in 2012 as a Maxine project, which goal was to create an object-oriented compiler. So compiler that is written in an object-oriented language, such as Java. And this was done in order to reduce the time you have to develop the compiler. For example, like a C or a C++ compiler, you have a really high abstraction in that kind of language, and you have to have a really good experts in those fields in order to create these compilers. While on the other hand, object-oriented languages such as Java, it's much simpler to create such compiler. So OpenJDKs project Metropolis. This presented the GraalVM virtual machine. So basically, this is a high-performance embeddable polyglot virtual machine in which you can use different languages, for example, native languages, JVM-based languages, and interpreted languages in the same runtime system. And this is currently being developed by Oracle Labs in Austria, and they are collaborating with Johannes Kepler University in Linz. So this is the basic architecture. This is a simplified version of GraalVM architecture. So at the bottom of the stack, the hotspot is hotspot VM. So this is a virtual machine that was created by Oracle, which became default in Java 1.3, and this is a really good virtual machine. A lot of time and a lot of money has been invested into this virtual machine. On the top of this, we have the JVM compiler interface. This interface is used to insert a compiler, in our case, high-level object-oriented language-based compiler, Graal. So it's also important to say that this virtual machine has a modular architecture, and this means that you can reuse a lot of really good stuff in a hotspot VM, such as memory management mechanisms and garbage collectors, but we can replace the C1 and C2 compilers, so server and client, from the hotspot and insert our own Graal compiler. The thing with Graal compiler is that it only supports JVM-based languages, like Java, Scala, Kotlin, Ruby, and others. But on the top of that, we have the Truffle framework, which allows us to implement many different kinds of programming languages. For example, GraalVM team already has JavaScript and Python, like a high-performance versions of those. And on the final layer, we have Solong. This targets the native languages, so LLVM-based languages such as C, C++, Swift, and others. So Truffle is, as I said, it's a way GraalVM implements different programming languages, and it is a part of GraalVM as a project. The most important things are the interpreters. So when you run a program, we create abstract syntax trees based on that application. So all applications have abstract syntax trees, and based on those abstract syntax trees, we create interpreters. And evaluation of abstract syntax trees is much simpler than to create an optimizing compiler, because creating an interpreter for a language is much more efficient and faster than creating a compiler. So for example, GraalVM team created a JavaScript interpreter, which has around 60,000 lines of code. That is a lot, but JavaScript V8 engine has over 3 million lines of code, and they have almost the same performance. The next thing is the partial evaluation. So this is a optimizing mechanism where Truffle uses Graal as a partial evaluator. And this means that at runtime, Truffle is gathering some information and adding that to the abstract syntax tree nodes. And based on that information, it is creating it is speculatively optimizing the system and creating a high performance machine code. And the last thing to say, so interoperability protocols. As I said at the beginning of the presentation, the problem was that at runtime, not all languages have all different tools that you want to use of the same quality. And at runtime, all interpreters from Truffle use the same interoperability products, meaning that at runtime, Truffle doesn't really see the difference between those programming languages. Meaning that all these different configuring tools, dynamic analyzers and such, can be used in a polyglot manner. So you can use JavaScript debugger in Java and really cool things. Another thing I would like to mention, so the Graal compiler. If you want to have a really good virtual machine, you have to have a really good compiler. And the special thing about this compiler that, as I said, it's written in Java. And that creates us a Java and Java concept. I won't go into much details with compiler because there's really a lot of things to say, but I'll mention the main thing of this compiler. So the Graal intermediate representation. This is the part where all high-level optimizations are being done, and they're all platform independent. So Graal IR takes the front end as Truffle or something else, and creates all high-level optimizations on that front end, and in the end produces high-performance machine code. And I would also like to mention the inlining and escape analysis algorithms. So this is actually the part where the Graal compiler really shines. It has a lot of other standard compiler optimization, but this one are a state of art. Now comes in my part in this research. So GraalVM offers 2 editions, the community one and the enterprise edition. Since Windows edition is still in beta phase, I used Linux in order to test all of this performance stuff. I use these two versions of Graal, and I use JDK 10 and JDK 11 in order to compare it. And I found a few really interesting patterns while testing this. So as you can see, GraalVM or GraalVM, either version, performed better in 5 out of 6 cases in my tests, except from the one. So as you can see, JIT at the end. The problem is that this is actually a single-threaded application, and this is the only time when Graal versions didn't perform better than the JDK 11. But also, as you can see, these two first test, Graal Community Edition and JDK 11 are pretty similar in performance, and also Graal AA and JDK 10. But also, the difference between two versions of Graal. So Community Edition and Enterprise Edition don't have really the same performance, and the Enterprise Edition always has much better actually performance. Because my guess is because Enterprise Edition has a lot more support, a lot of more time is invested into this edition. With that, I did also a lot of polyglot testing. So for example, I used Java's big integer and converted it into JavaScript, where I did some simple algorithms, and it worked with almost zero overhead, and it was really good. And also I created a Python function, and out of that Python function created good graphs in language R. And it seemed to everything will be working as expected. And there is a lot of other tests that are conducted by GraalVM team. You can check them out at their official page. So additional features. Graal application can be also packed as a native image. So inside GraalVM, there is another virtual machine called Substrate VM. And it has all other features as any virtual machine would have, but it can be packed really fast as a binary and deployed wherever you need it. And another feature is that it is embeddable. So this means that you can take a GraalVM as a whole, convert it into binary, and push it into some deployment. So for example, GraalVM team played little with it, and they created a binary from GraalVM and pushed it into Oracle database. And inside the database, they executed some kind of queries, and directly in the database on that queries, they executed some JavaScript commands, so JavaScript functions and such. And so they basically pushed business logic inside the database and skipped a lot of process when you have the query, get the data from the database, and do your algorithms and that stuff. So that's it. Any questions?
Okay. Hello, everyone. Thank you all for coming. My name is Paula, and before I start, I would firstly like to thank our professors, our mentors, for helping us with these projects and giving us an opportunity to be here today and present what we have been researching in the last 2 months. Okay, so memory management. Memory management in general is the process which controls the allocation and release of the memory. And you all know that in Java, this process is being performed automatically. So firstly, I will give you a short introduction about memory management. Then I will say something about current garbage collectors in the latest version of Java. Then I'll go on to discuss in more depth the additional experimental garbage collectors which have been included starting from JDK 11. And then I will explain how we performed the research, as well as you will be able to see the results. And of course, in the end, I will give you a conclusion. And if you have any questions, even during the presentation, do not hesitate to ask. Okay, so memory management, as it is performed automatically. The main goal of this feature is to control the objects in that way so that the memory which is occupied by objects which are no longer being referenced are being removed automatically. Also, so this memory management is achieved through garbage collection algorithms, and its primary principle relies on a market sweep algorithm, which is actually the underlying principle of all garbage collection algorithms. So in its simplest form, this algorithm stops all running application threads, and then it examines through the set of objects which have a reference in any stacks frame of any application thread, and afterwards it marks every object found as alive. Every object left is considered to be garbage and is ready to be collected or swept. Also, that's all happening in the runtime memory area called heap. So now my question for you is, do you maybe know how many garbage collectors are part of the latest version of JDK 12?
3.
3?
Shenandoah, Epsilon, and G1.
Oh, okay, yes, but including all, that would be 6 or 7 if we count parallel and parallel vault as the same collectors. Okay, so in addition to already existing collectors, which have been here since the beginning of Java, which are serial and parallel collectors, and also in addition to G1, which has become the default collector in Java 9, we have additional collectors, which are actually experimental, so ZGC and Shenandoah GC. So serial, parallel, and parallel vault GC are stop-the-world collectors, which means that they have to stop all running application threads in order to perform the collection. On the other hand, CMS or concurrent mark and sweep garbage collector and G1 are known to be concurrent. I mean, they are not fully concurrent because neither each of these collectors is fully concurrent, but the period of time when they have to stop the running application thread is only limited to scanning the objects. By the way, if you did not know, concurrent mark and sweep has been deprecated since Java 9. And another major difference between G1 and other collectors, I will say they are all collectors because there are many new implementations of these collectors, is that G1 has divides a heap in sets of regions, and all these old collectors divide a heap into generations, actually into young, old, and permanent generation. Okay, so as I have just said, G1 divides a heap into regions, which means that there is no need to decide in advance which regions will be part of either young or old generation. Also, the problem here with G1 is that it can perform collections on the whole heap, but that mechanism is known to be fail-safe because actually one single thread performs the sweeping, compaction, and allocation of objects when the full collection is performed. But however, since JDK 10, G1 has been improved regarding the worst-case latencies because it uses the same number of threads as mixed and young collections do when performing the full collection. Okay, now ZGC. So ZGC is known to be scalable and low latency collector, which means that it can handle heaps ranging from relatively small to very large heap sizes, and that does not have an impact on its post times. Also, it is only supported in 64-bit platforms. Actually, its main platform is 64-bit Linux. And the reason why is because it is achieving concurrency with two main core methods known as load barriers and colored pointers. So now I'll explain why it does not support 32-bit platforms. So colored pointer coloring or colored pointers method uses a 64-bit pointer to store the metadata about the object itself or about the object that it points to, and there is not enough space in a 32-bit pointer to actually store that metadata. With storing this information about the object, we can have a load barriers that can read that metadata and check what has to be done in order to move the object. So, for an example, if the metadata bits, actually we call it colors, are bad, there is that means that there is a need to perform particular action, whether that's remapping, reallocating, or marking an object, depending on the phase of GC. And good color indicates that there is no need to, again, load the object reference from the heap. And Shenandoah garbage collector, it is very similar as ZGC. It also divides the heap into sets of regions, and it is also low pause, parallel, and concurrent GC, which means that it can also handle heaps ranging from small to large sizes, and that would also not have an impact on its pause times. The object layout for Shenandoah GC is that it adds its word on every object's header when a particular object has to be moved. And in that way, it does not have to immediately update all object references, but it is able to perform a so-called atomic compare and swap method to have it point to new location. And in that way, all future readings and writings can be done on a forwarded copy with the forwarded pointer. Okay, so now I will tell you something about how we performed the research. So we have used the same, the Kappa benchmark version as my another colleague, Hrvoje, who is also here with us today, used when he actually started this research. I have chosen these 4 applications, particularly for this presentation. So PMD, Sunflow, and Xelan applications are multi-threaded applications, and FOP application is an application which performs in a single thread. PMD, I believe it analyzes the Java source code in order to see if there are some problems. Sunflow application is a rendering system that actually creates realistic images. And the Xelan application transforms XML document into HTML document. And FOP application simply generates the PDF file. In addition to these benchmarks, we have also used the GraalVM, which is a graphical tool to measure the number of collections as well as the time needed for the performance of that collections. Okay, so here are the results for PMD case and Sunflow case, and as you can see, G1 I have only wanted to show you the time used to perform this because we believe that's more important than number of collections in this case. And as you can see, G1 performed in a really decreased time in comparison to other garbage collectors. And as you can see, through different versions of JDK, its time for execution has significantly reduced. Also, for example, in this case, you can see a big difference in a case of FOP application, which uses the single thread, where G1's time has been For example, in comparison to parallel GC, it increased even 2 times more. But however, in Xalon case, it is again the G1 who performed in the shortest amount of time. And our conclusion is that even though G1 performed better in significantly reduced time in comparison to other GCs, if you ask me now which collector is the best, it really depends on the application. And because we didn't have an opportunity to measure the ZGC's performance time as well as the ZGCs and Shenandoah collections using the visual VM because it was not supported, it is still not supported. We, however, truly believe that those are new technologies which are worth exploring. And that's all. Thank you.
Any questions?
Okay, so you are measuring the time it takes for the GC to basically punch in and do garbage collection. Is that what you were measuring?
Yes.
But what you didn't say is how it relates to the performance of the actual application. Is it the same set of calculation that was performed? Because just because some GC takes longer doesn't mean that overall the output is going to be less.
You mean when comparing also number of collections, or?
It's not about that. It's about the performance of the app. So, for instance, were all the apps running 1 million PDF conversions, or what was the?
I mean, we have performed several iterations for every application.
Yes, but how long did that take? You understand?
Zero time for that. Thank you for your question. Just to jump in on this part. Well, actually, one thing here is that this whole experiment or research, however we call it, was run by the Kappa benchmark, which means actually in the Kappa benchmark you have the already preset applications predefined that you can try to use and see what happens there, and you run them in number of iterations. So you can set actually the number of iterations that you run this thing. You can set it to 10 or to 1,000. Actually depends on what you're trying to see. Of course, there's always some, let's say, learning period or something when those things have the time to kick in and to actually start working correctly. But honestly, the Kappa benchmark is not a real-life case scenario in which you can actually relate to, let's say, your application that you're running in a production or somewhere out there. So this is, in a way, a preliminary research in which we try to find out how do these GCs work together and which one in this relatively limited set of preliminary results is better or not. Honestly, we don't have, as Paula also said here, we don't have an answer, which one is better or which one should be better for your case. So I would say that maybe we can discuss it a bit later, but let's try to run a real case like if you have one, and let's see what happens there. Because honestly, this is a bit of a luck, Sometimes you see some unpredicted behavior of few of those GCs, and sometimes, you cannot know exactly what to expect. There still are no official guidelines, unfortunately, practically from none of these GC providers, as you may say, or people who are developing them. So I would say, let's call this whole thing still a work in progress. ZGC and Shenandoah, on the other hand, are experimental ones, and also still in JDK 11 and 12 now. So we would try not to, I think that's the best way to end this part. We would not try to conclude what's good, what's bad, what's best. We're just trying to tease you a bit, to try all these things and to see how they work in your case. But we can also help you with that because we tried it ourselves, okay? I don't know if that answers your question, but basically that's what we did. Okay, thank you. We can discuss it later, Mark. Thank you. Any other questions? Sorry.
Yeah, one.
Yeah.
How come you didn't try Epsilon? I think they made a garbage collection only for testing.
Yeah, I mean, we didn't want to include it in the research because it's made for testing purposes and it does not actually collect garbage, but it only creates garbage.
True, but it was made specifically so you can test how better some garbage collection is. because it's pretty much the zero case. It's the worst case, possible case scenario. Everything can be better from this. So you can easily compare garbage collectors based on epsilon.
It's like bubbles, sir.
Yeah.
Something like that.
And you're totally true, epsilon should be included and it's there in the future work. So yeah, we'll have a reference point with garbage collection that just does the garbage, like epsilon, and then let's see how the rest of the bunch actually does the thing there. So yeah, it's there. So it's still ongoing, you know, this is just the first preliminary results after 2-3 months that we are doing it. So yeah, thank you. Any other questions, sorry?
Did you try any commercial GCs?
Not yet.
There's some super interesting results you'll get if you try Azul's C4, continuously compacting, blah blah. Basically, everything is going to look like it's one time, like everything takes twice as long. The GCs will take 10 times as long, but the app will fly. There will be absolutely no latency, even though the app will be slower, and even though the GC will take much longer, but the users will never feel latency. So such a benchmark will never tell you about the user experience, because what you're measuring is the totality, but we're not measuring the latency. Yeah. Okay, but you can try it for free.
Exactly, you're totally right on that part, but Zulu was not the initial part of the this research. But as epsilon, I think Zulu, well, honestly, these days, like every month or so, there is someone talking about there will be some new garbage collector that will be better than any other out there. And C4 from Zulu is definitely the one to look into it, but we didn't take it in this research. Okay, thanks. Okay, thank you very much.